So homeostasis is the maintaining of a constant internal environment. For the human body, it's 37 degrees centigrade. pH of blood is roughly 7.4. Glucose in the blood is 0.1%. And we maintain these values by feedback loops. Now, body temperature doesn't maintain at 37 degrees perfectly. It actually fluctuates just around 37 degrees. A little bit too high sometimes, a little bit too low. Your body adjusts by it being high, dialing it down. And when it's too low, it dials it back up. The process is called a negative feedback response. So this process senses change, and then as a result, it does the opposite. So negative feedback has this connotation that it's always lowering, lowering, lowering. But the better definition might be it's doing the opposite. So you can call it opposite feedback if you like. So there's three components: the sensor, which is also known as receptors, the regulatory center, which is often your brain, and the effector or the response. And the analogy we like to use is the thermostat in your home. So if you're at home and it's early in the day and you're a little bit cool, you might go to the thermostat. You being the sensor have decided it's too cold. You go to the regulatory center and you turn up the dial. So over the day, the temperature would go up, right? And in the afternoon when the sun's out, you might say, well, now it's all of a sudden too warm. So you as a sensor detect that it's too warm, and you go to the thermostat and you turn it back down. You do the opposite. As it moves into the evening and the sun sets and it becomes cooler again, you might detect that it's too cold, so you do the opposite and you dial the thermostat back up. And this would repeat over and over again. Now, if you did this with minor fluctuations, the temperature in your house might be really close to a constant 20 or maybe 21 degrees. But more than likely, it fluctuated above 20 and below 20 and above 20 and below 20. So these small fluctuations, if we were to look at the details, the microscopic values, you would see that they fluctuate up and down. But if you step back and just look at maybe the integer values, it would be a constant value. And it's similar to how the horizon, the mountains, and the shore or whatever you're looking at would undulate up and down. But as you back away from it, you can see that it gets flatter and flatter and smoother and smoother. Another way of thinking of it is a teeter-totter. So any of those homeostatic values such as temperature, pH, blood pressure, 120 over 80, it would go too high and your body as a response would dial it down. And then it's too low, so your body would do the opposite, negative feedback, and dial it back up and down and up. So you're aiming for this homeostatic value, but you're actually fluctuating up and down around it. And this is achieved through negative feedback. Blood pressure is another example. Blood pressure as you're exercising causes your heart to beat more firmly and more fully. That increases blood flow, and it causes pressure on the arteries and veins. You have receptors in your arteries that detect this pressure every time your heart beats, and it will send a signal to your brain, the medulla oblongata, a portion of your brain by the brainstem here, right here, which will respond by sending out hormones that will cause your blood vessels to dilate. So going from a small diameter to a large diameter, which reduces the blood pressure. Now, if your blood pressure drops too much, another signal from the receptors in the blood vessels will send a signal to your brain saying it's too low, and your body would respond by producing hormones or other types of signals to contract, to narrow the diameter of the blood vessel, increasing the blood pressure, and so on and so on. So your blood pressure of 120 over 80, which is ideal, would probably not be a fixed value throughout the day. It would vary a little bit too high and a little bit too low, and hopefully right around those two values of 120 over 80. Another example is blood glucose level. When you have a meal, all of that blood, all of that sugar will be absorbed into the blood essentially all at once, and that can be a bad thing. Too much sugar in your blood can cause you to suffer from diabetic shock. So what your body does is the pancreas secretes insulin. And insulin allows for the liver, the muscle, and the fat to absorb and store the excess sugar, so your blood glucose level remains near 1.1%, sorry, 0.1%. And when it's time for that sugar to be released, if you're exercising or doing work or just for maintaining your normal metabolic reactions, glucagon would come along to help release that sugar back into your circulatory system so it can travel to the necessary cells to convert it into ATP energy and do work. And that would be a slow trickle of release of glucose so that your body's not shocked by a flood of sugar all at one time. Feedback inhibition, we talked about how metabolic pathways are not often just a single step. In this case, it's a 1, 2, 3-step process from substrate A into B, C, and then our final product, D. Now, in feedback inhibition, as the final product builds up in concentration, it may have this ability to self-regulate by blocking enzyme 1, 2, or 3 from proceeding, so the concentration of D subsides or falls. And as that concentration of the final product falls, this feedback inhibition can be reverted or released, and enzyme 1, 2, or 3, whichever enzyme it's feeding back on, can go back to fully functioning. Another example would be this one, which is a little bit more complicated, but it shows you where the product D inhibits, feedbacks to inhibit. And in this case, you have substrate A, and it can lead to product D or F. And you can see a buildup of product D can cause an inhibition of enzyme 2, which reduces or self-regulates so that the concentration of D does not get out of hand. If that's the case, concentration of D will fall. And because there's an adequate supply of substrate A, more than likely product E and subsequently F will go up. But as concentration of D drops, the inhibition on enzyme 2 would be diminished or released, and more product D would be produced. Therefore, product E and F would probably respond by in the opposite direction, and there'd be a little bit less of that. Positive feedback, although it sounds like you're always adding and adding and adding, and our examples we do talk about that, but this is the mechanism which keeps us from maintaining homeostasis. It creates a greater change. It promotes more of the original stimulus. Our two best examples of this is fevers. When your temperature rises, your body might detect this, and in usual circumstances, your body will respond by cooling it down. But when it comes to fevers, your body wants more of the fever, more of the temperature, and it would positively feed it back, saying more of the same, please, and it would rise. Now, it's only rising not because it's positive, right? It's rising because it's more of the same. Another one would be childbirth with contractions of the uterus. They come on mild, but as a result of childbirth and the contractions would strengthen and instead of subsiding, and the subsequent ones would be greater and greater until they're adequate to help birth the child. An example of positive feedback that might be not more of the same in the positive direction would be sleep. As you get tired, your body may actually decide that it needs more and more of the same, that's making you more and more relaxed. So that's more of the same in a downward direction when it comes to energy. So positive feedback is not necessarily always up, up, up. It can be down, down, down as well. Positive feedback can be described as more of the same, where negative feedback means do the opposite.